Hello, everyone. Thank you for joining me today. My name is Shin, and I'm here to present our study on the impacts of symbolic regression-integrated physics classes on students' perceptions of using machine learning in science. I am postdoctoral researcher in Ewha Women's University, and I conducted this study with Jinseop Jang and Soojeong Baek. To start with the background, as AI becomes increasingly integrated into education, Korean government policies encourage the use of AI, such as machine learning, in the science curriculum. Machine learning models can enhance learning but are often complex black boxes, which limit students' understanding and trust in them. Our goal was to engage students with machine learning, especially symbolic regression, to explore scientific data-driven discovery. Let's briefly look at symbolic regression. I will call it SR from now on. SR is a form of machine learning that identifies mathematical equations to fit data. Unlike traditional machine learning models, SR gives us interpretable equations, helping students see the relationship between variables more clearly. We used the Technology Acceptance Model, TAM, to assess students' responses and identify their perception of using machine learning in science. This model, widely used to understand acceptance of new technologies, and is based on two key factors: perceived usefulness, how much students believe the tool improves their performance, and perceived ease of use, which measures how easy they find it to use the tool. Additionally, we expected four external variables to be influential on students' perceptions: machine learning background knowledge, attitudes towards general technology, career-relatedness, and expected effect of using machine learning in science. So our research focused on two main questions. What impacts does SR integrated physics classes have on students' perceptions of using machine learning in science? What factors significantly influence students' attitudes and perceptions of using machine learning in science? Our participants were 41 high school students in South Korea, consisting of 35 females and 6 males. They participated in an average 7-hour physics class integrating SR. Using tools like Tracker and Python-based SR code, students collected data and ran SR algorithms to derive mathematical equations that explain real-world physics phenomena. For example, parabolic motion and damped oscillation. To assess students' attitudes and perceptions before and after the course, we used pre- and post surveys. The survey included 25 questions based on TEM theory. For the analysis of these survey responses, we applied path analysis. Additionally, we conducted semi-structured interview with 5 students both before and after the course to gain deeper insight into their individual experiences and reflections. Each interview lasted around 50 minutes. To analyze the interview data qualitatively, we used the constant comparison method. Survey results indicated that perceived ease of use had a minimal effect on students' attitudes toward machine learning, while perceived usefulness played a significant role in shaping their intention to use these tools in science. External variables like career relatedness and attitudes towards general technology were also significant in shaping students' acceptance of machine learning. Using constant comparative analysis, we identified 3 themes from the pre-interview transcripts and 4 themes from the post-interview transcripts. To summarize, before the course, students largely had a second-hand understanding of machine learning, trusting its efficiency and accuracy without fully grasping how it worked. They saw it as a useful tool for science. After the course, their views became more realistic. They realized the significant human time and effort required, recognized the risks of relying on tools they didn't fully understand, and developed a more cautious, critical perception on using technology and data-driven approach in science. Specifically, in pre-interview, most students lacked significant background knowledge or experience with machine learning, but they believed its efficacy and accuracy. Additionally, in pre-interview, students showed blind faith in the advancement of technology. One of students said, "I think it's okay to keep using it with experiments, even if they aren't perfect now. And if the research shows there's no major risk, I believe it's fine to use it." After the course, students realized that using machine learning requires significant human effort and time. Some students expressed frustration, saying it felt like hitting a brick wall due to the amount of grunt work involved. This new awareness helped students understand that while machine learning can offer powerful tools, it doesn't eliminate the human element in scientific research. Many students developed a cautious stance on relying too heavily on machine learning outputs without understanding the underlying process. A student mentioned, "I feel like we shouldn't rely on it entirely, not blindly." Another student said, "I began to think the risk might be greater than I originally expected." In conclusion, our research suggests that students' positive attitudes towards technology and career relevance increase the likelihood that they will accept to use machine learning in science. The SR integrated classes allowed students to experience the usefulness and limitations of machine learning firsthand. They found the process challenging yet rewarding, and by actively participating, they gained some kind of literacy of what it takes to integrate these tools into scientific research. However, the course also shed light on the importance of fostering critical thinking skills alongside technical skills. Students recognized the efficiency of machine learning, but also began questioning the accuracy of results when they lacked an understanding of how those results were derived. Our findings underline the importance of designing science education programs that don't just introduce students to new technologies, but also teach them how to critically evaluate and effectively use the tools. Thank you for your attention. We hope our findings provide you insight into integrating machine learning in science education and the shifts in perception that can occur among students when advanced technology is introduced into science classes.